Okay, so welcome to class, and also speaking to the folks here too. So it's November 6th, 2024. Today we're going to talk about density and interpolation. But before I do, we've got a guest here. This is Dr. Ansari. He's one of our postdoctoral researchers, so he's got his doctorate. His focus is on remote sensing and a lot of other things here. But I wanted to introduce him here. I wanted him to talk to you about some of the things he does, because if you want to see what he does, I think he's going to be involved in some raster GIS and doing some other things next semester. But I wanted to introduce him. If you want to work on papers, we already got a paper out, and we're working on some other things with flood assessment, especially some of the things that are happening out in Western North Carolina. But I want to introduce him and him talk about some of his research for a little bit. If you're interested, you need an advisor, because he can be an advisor here. He can definitely be a graduate advisor, or he can be on your committee. So without any further ado, let Dr. Ansari talk a little bit.
Thank you very much. Good afternoon, everyone. So I'm Rizwan, basically postdoctoral fellow in the department. Right. So at present, my work is related to the flood damage assessment, which happened recently in Western North Carolina.
I want to just move out of the way, so we can. Like, they're looking at the screen, so you can go that way or that way.
Okay. So basically, what exactly at present I'm using some Landsat data to assess the damages because of the flood, especially in Buncombe County, in the near the in the surroundings of Asheville. So what exactly we are trying to do is, what is the level of damage we have, right? So there are some GIS data also available. So we have taken a pre-event and the post-event data, basically, so to see what changes it basically has caused, right? So a few examples we have. So this Landsat, people, I hope we are aware of the Landsat characteristics, right? So at present, the target is on the Landsat data, basically. So what we do, basically, we have these patches, the data available from the USGS, right? So the target counties are basically the McDowell County and the Buncombe County here, right? So this is a pre-event data we have. Similarly, we have the post-event data, basically, right? And what is the target, basically? We are trying to compute different indices. So we are aware of different indices, like what happened to the water flow, what happened to the water reservoirs, streams, right? And in particular, vegetation, or the if there is a spatial damage, right? Maybe the building collapse or partial damage or anything like that. So at present, like what I'm demonstrating here is one county, only one county. Like pre-event data, and we have a post-event data, and what's happening basically to these regions, basically. So this particular Landsat data is a 30 meter by 30 meter spatial resolution data. So we may not be able to get very fine details or changes happening. So for that, basically, we are trying to acquire some data from Sentinel or UAVs, right? Because we investigated, we found that during the event time, 27, 28, and till 1st of October, the landscape was not very clear. So whatever the images we are taking from the Landsat, which is optical data, so that is not very clear, right? So for that reason, our motivation is to go for the Sentinel or the radar data. So if you are interested in working with that data, you are welcome, right? And we can have a collaboration for these applications. So this is not only one application, but this is only one application, right? We can come up with many other applications, and if you have any idea in your mind, right? So these are some results like which we generated NDVI calculation in McDowell County, basically. So apart from that, we have some GIS data where we are collecting these points, which are the points or the buildings or the areas which or the bridges which got destroyed completely, majorly affected, minorly affected, right? So that the idea is to combine the raster data with the GIS data, and we are also we'll be visiting in a couple of this week, one of the days for a field trip, so to get the ground truth images and integrate that particular information as an independent source to integrate the GIS data, whatever we have collected that part, Landsat, and if possible, Sentinel and UAV SAR data, right? So if you are interested, right, so we have some other samples as well, like these are the water streams basically which we collected, water streams and water reservoirs in these counties. So this mapping will be done basically. So if this work interests you, right, you are welcome. So thank you. I will not take much time now.
No, it's fine.
So if you are interested, you can drop an email. Right.
And next semester, we're teaching a raster GIS class, and in it, basically, raster is when we represent data as cells, like elevation. So we use raster data just to model water, because what direction does water go? It's down, wherever gravity tells it to. So these visual elevation models combined with some of these indices are really good indicators to look for water flow and, more importantly, water accumulation. But with lots of water behind it accumulating, we can use that. But we teach a class next semester called Raster GIS. It's a graduate level class. So, I think Dr. Ansari will probably be involved with that a little bit. And but this is some of the work he does. I strongly encourage student participation, student research, especially PhD students who, you gotta get your 3 papers and, knock some of these out quick, like, quick. I've given, Wilbur and Philip some pep talks on, position paper, and I think teaming with Dr. Ansari on some of these things with the raster GIS class will be, beneficial. You just might need some, socioeconomic data analysis on this and names on the papers. Do you have to be first author on the paper? Which not?
No.
Just give your name on the paper. So if you could add some important parts to the paper, these days, I pay for stuff that I didn't, put my name on the paper, but be a pertinent part of it. You don't have to be the expert on the NDVI and all those other things, but I see GIS data sitting right there that we all know what we can do things with. So please reach out to him. His office is around the corner from mine. He strong researcher, and he complements a lot of our strengths on campus because in this department, because he's really good at LiDAR, raster data, which are things I'm not necessarily very good at. And we have another instructor who will be working with the raster GIS class who's got some skills in it. This is the go-to person when it comes to raster data. So please take advantage of this valuable resource while he's here for the next couple of years or until someone swoops him up with a 6-figure salary.
You want to see your contact? I'm so
I'm
sorry.
sorry.
I missed you. Thank you.
Yep.
That wasn't so bad, was it?
No, I just, I wanted to keep it as short as possible, so
No.
that's next time.
No, I appreciate it. Thank you. Okay,
Thank you.
next.
Okay, thank you, everyone. Thank you.
Safe travels home.
Thank you, sir.
Yep, thank you. All right, and I'll see you Monday because I'm heading to Greenville on Friday and hopefully I'm working from home tomorrow.
Okay, thank you.
If all works. Okay, thanks. Right, and we're pretty lucky. Our department has 3 postdoctoral researchers, so they got kind of diversified skills. Basically, postdoctoral researchers are typically positions that you want to take after you get your PhD. If you can't get a teaching job, which are harder and harder and harder these days. I know how hard these are. So what we have, I posted the things last week. Did I have class at home last week?
Yeah.
Okay, all right, sorry, but I get this all mixed up. I had some sick kids and it was yuck. But last week we talked about models. Daniel's had some really good questions about which models to use. Should we use OLS? I'm kind of meat and potatoes OLS because it's truly mathematical, but has the generalized linear models that ArcGIS Pro is offered. So if you kind of start increasing, you can start getting newer and newer versions of ArcGIS Pro. It's really starting to get into the grouping and the modeling and the OLS. And there's something called stepwise regression. Dr. McGinn's pretty good at that because he utilized that for his dissertation, which you can bring data into either R or SPSS. So stepwise looks at different combinations. So if you have 20 or 30 different variables that go into something, it'll say, hey, we can't use variable 7 because it's directly related to variable 6. So it'll get rid of that and then look at combinations. Look at 1, 2, 3, and 4. So we can find the best R squared and the best associations with those. But some other things that you can add, to me, these are powerful visual graphics, are in Excel, we can make the nice little scatter plots. And I think I showed these before, especially with the regression, but we can make nice little scatter plot. This was the example that I talked about in class. And you can click on the actual data. So you can click on the points and it'll say add trend line. So you can click on add trend line. We can add the linear right there. I was trying to be a little fancier where I add the polynomial or the logarithmic or the moving average. And I can click on add R squared and it'll put in the little equation. Remember the equations, all those, I think this is parabolic right here. So 0.0833 x squared plus 2, that nasty thing. And all this is just part of a parabola. We know the parabolas that kind of look like that, like y equals x squared or whatever, because y is never going to be less than 0 unless you're working with imaginary numbers and all that other garbage. But this is just part of our parabola right here. But we have moving averages, linear, which is the y equals mx plus b that we spoke about, logarithmic, and exponential. Raising something to the x power. And you can fit those nicely so you can kind of manufacture better and better R squares. But this is all stuff that you can do directly in Excel. And to me, these are powerful visuals and graphics that we can look at. I think we have one more assignment and then we're kind of done with the assignments and we're getting into the position paper. As you notice, I like the position paper. I always encourage folks, use this position paper for a journal article. Now, master students, journal article doesn't, it's good to have, but PhD students, you need 3 journal articles. I'm on something, I'm one of the editors or one of the reviewers for something called the North Carolina Geographer. So if you do something in North Carolina with geography and maps, I'm going to look at it and I'm probably going to pass it. I'm probably going to say, nice job on it. So those are some low hanging fruit because I think even with faculty members, and we'll start to sound like my parents a little bit, but even with faculty members, and I'm on our college's review committee, PTR or not PTR, was RTP, retention, tenure, and promotion. I'm on the committee. We see so many people that have been here, 5, 6, 7 years and still not knocking out papers. And those are all things that we kind of go in knowing I gotta get 3 papers done over the next 7 years. And a lot of times we, me part of the committee, need to tell people, no, you didn't do 3 papers. I can't make up a paper. And so these are things that are really important, especially in academia. I don't know why, they probably shouldn't be important, but I don't make the rules. So I just need to kind of abide by those. And so these low hanging fruit here, even faculty kind of get stuck with, take the advantage, knock out some papers right here, low hanging fruit. Like I tell people, it doesn't need to be good. It just needs to be, good enough. Go save the world when you're making 6 figures instead of, them paying you $1,500 a month or $2,500 a month or whatever you're making here as a poor graduate student. Okay, so you're seriously, go do it. So turn these things here, turn what you're doing here into some good work, and you're going to be recognized. Cameron's sitting here. I'm going to embarrass him real quickly. But we have something called the Herb Stout Award, which is part of the North Carolina GIS conference. And that comes up in the middle of March. I plan on taking a bunch of students here, those of you who are interested, because it's over in Winston-Salem. It's one of the biggest state level meetings for GIS professionals, and we see former students there. But we have the North Carolina GIS Conference, and we have something called Herb Stout Award, which is, we have an undergraduate nominee and a graduate nominee. And Cameron's gonna be our undergraduate nominee, where he gets free admission and like $200, $250 check. And he gets to present, and he gets to present there and represent NCCU. I think Chima, I know Chima's been in and out with illness, but I think he's submitting something there, and then I submitted something on Andy's behalf. So Andy will be presenting there in March as well. Thank you, Andy. Thank you very much. And so that's kind of what we call volunteering people. He's going to be submitting there. But it's every other year. It's a big, and the graduate nominee is an online student who lives out in Nashville, and she's done some really good work. And we're going to look at a lot of things she's doing here, because she focused a lot of her work on spatial interpolation, extrapolation, and density mapping, which we're talking about today, because today we're still continuing on with predictive analysis. And she's an online student, started somewhere like UNC Charlotte, didn't work out, and she worked some type of weird second or third shift, like 6 p.m. to 4 or something like that, but she has done some really, really good work before us. I don't think I've ever met her in person in real life, but I will at the NCGIS conference. So we meet online a lot, but some really, really, really good work, groundbreaking work that I thought was impressive and warranted some of this. And, they're the best of the good work that we have going on here. We have some really talented, amazing students. We got some great Python work that, Andy's doing, and some of the neat things with fire stations, emergency shelters that, I think the possibilities are limitless, because a lot of it really hasn't integrated the GIS component with it, the spatial component with it. So I think there's a lot of potential there. So that's kind of my rah pep talk for, knocking papers out. It's, always good to kind of get these things out and kind of get you thinking on some directions that you want to go. Like Daniel, we got a project. This is what you got to do what we got to do. There's not a lot of leeway, but we're trying to looking for, places for synergies, places for leeway where we can really kind of take off in these different directions. Okay, so this was what we talked about last week here. I kind of posted some descriptions, different types of regression models, R-squareds, trend lines, all that other good stuff. And then today we're going to talk about spatial interpolation. So we'll talk for a little bit. And then this is the stuff that Caitlin did, which I'm really impressed with. We're still in the place where we're doing predictive models. Basically like last week, we can do a graph, and I think for the final exam, I think some sort of graph between height and weight. If I know your height, you can predict what someone's weight's going to be according to some model. And then outliers are going to be people who are, shorter and heavier, or taller or thinner or whatever, based on that trend line, if you think of it. So if I said your height is this, I can basically predict your weight pretty well, unless you're one of these outliers or where you have these really high residuals. And so what we're looking at today here is we've got temperature values here, and we're going to go back to some of the air now data, air quality data, not the recent stuff, some older stuff right here. But I can see some temperature stations here. I see down in Lake Lure, it's 88, it's 83 over here. It's 80 up here in Great Craggy Mountain, and then over towards Asheville, I got 82, 83, 83. What is the temperature in Asheville? What do you think it's going to be? 82, why? We got 80 in the mountains, so we'll go in that direction. It's a little slower. Up at the top of Mount Mitchell, it's 64, so that's a bit of an outlier just because it's more than a mile high right there. But closer to 82, why not 88? Because these are 88. We'll look further away. What's the confounding factor here? It's distance. That's all it is. It's distance right here. And I bet you most of the people said the 82s and the 83s are close to Asheville. So that's probably gonna be close to Asheville. This is kind of the whole Tobler's first law of geography. Things that are more related to each other are closer than things that are further away. And especially with physical phenomena such as temperature, this kind of plays right into that. And so we can kind of guess what it is. Now, when we represent surfaces, we have a lot of different ways to represent surfaces, represent spatial reality here. To me, we have these things called points, and back when I started like GIS back in, back in 1998 or whenever it was, these things were what we call lattices, kind of like fishnets. So this approximation of points here, but we started to turn these into grids where we zoom in, and these are just made up of tiny little pixels. And that's what Dr. Ansari is really good at, where that, well, it could be a reflectance. He used the word reflectance. What's reflectance mean? What is it? It sounds pretty obvious, like reflectance, but what do we measure reflectance in? What are the units? And because when I take a picture with my cell phone or I go and fly a drone, I take a picture, you zoom in, it's just a color, right? It's a combination of a red, green, blue, 0 to 255. It's a 3 byte image. But when we talk about reflectance, these are actual wavelengths, because he had this graph at the beginning that I thought he would have talked about a little bit more when we look at the different wavelengths. And most of these wavelengths your eyes can't see. So when we look at the reflectance, what reflectance is it here? Because look at this. This is blue. You turn out the light. Can you see what color it is? No. But we can also look at other wavelengths that we can't see. We have something called thermal. I have a thermal extension to my camera where it takes pictures, and I'm sure thermal is really, really big with fire. The problem about thermal is that it's emitted as opposed to reflected, because if I were to turn out the lights, you could see my thermal coming out, but you can't see the color of my shirt, because what's the light source? Lights. Now, what's the light source when we look at this Earth observation, that big orange thing in the sky? The sun. Exactly. Which serves it. And so that has confounding factors with the cloud cover. And that's what Dr. Ansari was talking about before. Like, we're looking at the before and the after with the floods from, literally like a month ago. And if the clouds, you can't see it because of the clouds, you're going to have to wait for the next time the satellite to come over. And that satellite is called Landsat, and it covers the Earth about once a week. Does that sound right? This gets out of my skill set a little bit. About once a week right there. So if you miss it because the clouds can't see anything, well, you're going to have to wait another week. And so it's come, afterwards a few times. But we have grids, we have something called pins, triangulating regular networks, and then we have contour lines. And so we see these. Now, basically, when we do density mapping and spatial interpolation, we're essentially creating raster surfaces, even though they represent two different things. So a density map, we can create densities from existing point layers. To me, I like that because we can show all the crimes. If I show 20,000 crimes, it's just really hard to see because it's 20,000 points. So I can create a heat map, a density map. And so we create a density map right there to do that. We already did density maps, right? We counted the number of cancer deaths within each county, right? Here we're doing the same thing. Didn't we also do that with quadrant analysis? And we just created those nice pretty quadrants because, well, they're all the same size. So I don't have to go and calculate density because they're all the same size. So if one of them has 8, another one has 7, I know the one with 8 has a higher density because they're all the same size. Okay, so they don't need to be normalized. So density, we can show where point and line features are largely concentrated. I largely focus on points, where interpolation, we calculate or estimate missing values based on some known values. And so like we saw before, we kind of guessed that Asheville was 80, 82, or whatever it is based on the values around it, where that space and distance are confounding factors. And so it uses various algorithms to compute new values. More values, we have better estimates. So things that are further away are going to get really wacky really quickly. And this is the example that we were talking about with the PhD students. Maybe I'll bring that example up if I can think about it on one of the rotations where we're looking at something called air now, which is air quality, ozone. What else is there? PM stuff, PM 2.5, PM 10. I'm just looking for people to nod their heads because this gets out of my skill set. But all the junk in the atmosphere, and then we kind of did a little bit of GIS magic so we could put it on a map and then fill in the rest of the state, because you only have about 21 places in the state where PM's taken. So you got to figure out where all other millions of places there, what those values are. So when we look at a density map right here, we can create a density map for maybe heart disease incidence. So we can create a search radius, and that thing is called a buffer. We ever heard the word buffer? Okay, typically we can do buffers, and we can take 40-10, or you take some more advanced GIS classes, but it shows patterns better than many points, but it smushes the data. And when we make a map, you're essentially smushing the data, but it counts the points within a certain distance or shape. And we can do things called kernel density. So when we look at something like cardiac disease, death, where are most of them? Most of them are right here, and I can create a density map that does that. Now, once again, like we have with our raster calculations, there's a lot of different parameters. We already kind of did some of this with some of our PhD students, is that most of them are here. There are a few of them that are here, but basically, I'm going to go to this cell right here. I'm going to count the number around here. Move over a cell, count the number around there. Go over a cell, count the number around there. How big is a cell? Boy, that's what you get to tell it. Okay. Now, when you take a picture with your camera, what's the resolution? That's that word resolution. When you buy a new phone, you're basically buying pixels. So you can zoom in and make out features or whatever. These days, my drone is like 5,000 pixels by 4,000 pixels. It's 20 meg. It can get really, really fine, especially if you're close. And when we take some of this drone imagery from a couple 100 feet up, we're at like 1 centimeter resolution, 4/10 of an inch or so. So, but we can calculate these because most people don't like looking at these data, especially things like crime or really high incidence. Now, your fire stuff, 100 points there, that'd probably be pretty neat to look at. And then we can start looking at the densities and associations with those. Because after the break, we'll talk about one of the papers that I have, because we can set up all the input features. We can set up search radius. We can see if it's circular neighborhoods, because essentially, if you think of all the grids here, we're just going to go calculate the density around a certain distance, go over to the next cell, calculate everything around, go over to the next cell, calculate the distance around everything around. We can create something that looks like this. This is really truly a mathematical surface based on those. We can also calculate something called kernel density, which kind of looks a little bit neater or prettier or whatever here. But essentially, this is what we're doing right here. We have a cell right here, and we just calculate however many are around it, the next, the next, the next, the next. And so when we look at this density mapping, some of the parameters that we can set is something called the mask. We'll talk about that mask today. I know the PhD students all know about the mask, so we can make things look nice and pretty because they're aesthetically pleasing. Output feature location, where do we store things? These days, we're all working with just one united folder here. I created a folder called exercise 8, a database called exercise 8. Everything's going to be stored there. The output cell size. If we make the cells smaller and smaller, increase resolution, what does that do to our file size? Increases it. Okay, so how many pixels do you want? How many pixels are necessary? If I'm creating elevation data, do I need elevation every meter? How about every mile? Definitely every mile. Every meter, that's kind of coarse, because I got 1,000 meters by 1,000 meter at one meter pixel resolution. That's 1 million pixels. Storing 1 million of anything is a lot. And that's barely campus right there. Now, when we work with some of the weather data, the temperature data from NOAA and NASA, what's the resolution on that temperature data?
30 by 30.
30 by 30. That's for land cover. For temperature, I think it's 3 kilometers. 3 is about 1.8 miles. Because how much does your temperature change? Does it change every 10 meters? No, not even every kilometer. So it changes fairly gradually. So we don't need a real high calculation. Now, if I were working with elevation data, 3 kilometers, and there's a lot of things that can go on in 3 kilometers. So you need to find that happy medium between finding this. And you'll hear the term out there called LiDAR. Has anyone heard that term LiDAR before? Light detection and ranging, where that we can create like elevation data with probably like 1 centimeter resolution. We really need that. I don't think so, it's, but there'll be situations like when we do something called indoor GIS, especially engineering and CAD and drafting and all those other things, surveying, we do need those. But search radius, units, area units, because when I did my bear analysis, remember that bear paper I did a while ago? I set my search radius to be, I think I set it to be like a mile. And it's because like the bear habitat is only about 3 square miles. So my radius is a mile. What's the area of a circle with a radius of 1 mile? Pi r squared. So r squared, which is 1 times 1, which is 1. What's pi? 3.14. So the average bear habitat is about 3 square miles. It's got about a radius, assuming it's a circle, radius of about 1 mile. So I created those, bear density maps. The habitats to be about radius of 1 mile. Because they're about, some science person went and figured out that the bear habitat's only about 3 square miles. I didn't do that. I just brought it into a GIS. And so we can do things like this. We have point density, we can do circles, because I've got maps like this. These are my deer vehicle collisions. This is some research that we did previously. And so I can turn it into a map that looks like this. This looks probably a little bit prettier than this. And then I can group these, I can average these by quadrant right here. Okay, so instead of doing a point count right here, where this is 6, 2, 5, 0, 1, I can give this a density, and it's going to have more. The word is granularity. Has anyone heard that term before? Granularity, basically meaning, well, the only possible values for deer vehicle collisions are 0, 1, 2, 3, 4, 5, 6, where this one could be 0.00723, 0.41529, 0.6. So instead of having maybe 11 unique values, I might have 723 unique values, one for each of the quadrants that we have right here. Now, in some cases, like with quadrant analysis, your only options are 0, 1, 2, 3, 4, because what are we doing? We're doing the number of cells. You can't have 4.27 quadrants. It could be 4, it could be 5. So we use those rounding algorithms, but essentially we use those so we can match those up to a Poisson distribution, which is basically a type of random distribution that we have here. Because when we do this by quadrant, there's only 13 possible values that you can have. 0 all the way up to 12. Right? Only possible values that we can have right here. As opposed to however many quadrants that we have here when we go through and average up the density. Because from these, we can go and do some calculations. Now, next semester, we teach a class called raster GIS. And so from these, I can say, hey, let me look at anything where the collision density is greater than 0.75. 0.75 deer vehicle collisions per square mile, whatever units we're working with. And so now I can query out all the deer vehicle collisions where they are 1 or 0. What's 1 mean? True? What do you think 0 means? Well, right? And that's what we call Boolean algebra. Have you heard about the 1s and the 0s? Basically, your bits and your bytes and all that other stuff are just 1s and 0s. I talked about RGB. Red, green, blue is basically values from 0 to 255. Is it so special that we have 255 different numbers right there, 256 different numbers? But why not 242? Why not 231? What's so special about 255 or 256? How many people follow tennis? No one at all. So in like Wimbledon and all that other stuff, there's 128 people. What's so significant about 128? Why would they have 128? What's that?
Yeah, matches down to.
Yeah, pair matches down to 1. So what's 2 to the first power? 2, 4, 8, 16, 32, 64, 128. You gotta win 7 matches. Exactly. Now, what's 128 plus 128? 256. And then how many of these things here? I got 1, 2, you got 8 of these, and these things are called bits. And so these are what we call byte. So byte. Okay, so basically I can store any color using 3 bytes. Okay, so possible values. So that's called Boolean algebra. Not invented, but it's underscored by an English mathematician called George Boole. You know, because when we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, what do we go to? 10. And then 11, 12, 13. When we count using binary, we go 0, 1, and then what do we do next? Well, 1's the highest, so we got 10, 11, okay, 100 or 100. We don't call it 100, 100. Because basically, what is 125? Really, what is it? 1 times 10 to the second plus 2 times 10 to the first plus 5 times 10 to the 0th. What's 10 to the 0th power? 1. Exactly. It's a special number, 1. That's all it is, right? So if we start counting base 5, base 7, base 16, it's the same thing. There's a whole different direction you can go with some of these things. The significance of 1s and 0s. Now, back in the day when I watched basketball, it was called the 64. You know, 64 teams. Why? Because each team had to win 6. Now they have this little money grab where they had like the 4 teams that go into the bracket that play on Tuesday or whatever. You know, but it used to be 64. Why? Because 2, 4, 8, 16, 32, 64. So each team had to win 64. I don't want to get, bore people too much with these, but this is kernel density maps right here. So these kernel densities basically just make it a little bit smoother. So these things just look a little bit smoother because all we're doing is turning these points into density maps. Because I think a lot of times most of us understand what this is. Okay, and especially when we have something like this, we can do this. Now, what are some of the trade-offs? What are some of the problems with a map like this? There might be a lot of people that live here, right? And when we're doing our quadrant analysis, or we're doing our density analysis like we did with week number 1, where we counted the number of cancer deaths by county, we went and normalized those by population, where in this case, we might not, we're not. But, if you're a resident, are you caring about, I want to look at the crime density, or I'm just looking at the carjacking density? I don't care about the number of people there. Okay, or deer vehicle collisions, because the bear or the deer is not going to care. A lot of people live here. I better go here so I can increase the density. Okay, and so some of these are really not pertinent, like especially things with like wildlife. They're not necessarily pertinent to the boundaries, like census tracts and block groups and counties that we define, or that crimes, in some cases, we can make crime maps like these. In other cases, we do normalize them by population because we know how many people live in a block group or a tract, where that a little square gets really ugly really quickly. Other things that we do now, we want to interpolate to raster. So it's somewhat like density mapping, where that we're going to create a raster surface, but we want to create all brand new values based on existing values that will not be there. To me, there's a lot of neat potential for people exploring the different algorithms, automating this. In data science class, basically we redo this exercise in Python. Now, you're not going to be writing Python from scratch. Basically, we can create models, we can drop and drag, and that's what we're going to do in data science. Drop and drag all the point and click things that we do. We can drag them into a template, and we can just get a little model to just run it, and then we can convert that model to Python. Not Python, it creates Python for us so that, look at all this programming I did. No, you didn't do the programming. It did it for you, but you take credit for it all you want, and then you can cater it however you want. So we want to create new values based on this. So we have a number of different parameters right here. And so we've got Z values here that we don't necessarily have with density maps. Now, in math class, what does Z mean? We've got our X, or we've got our X, we've got our Y, and what's our Z? that way. So some type of elevation, amount, or whatever. Okay, where that with density mapping, we're just looking for the concentration of points and in some cases lines. Now, a lot of times I leave all this stuff blank because that's what we're going to do today. But when we interpolate to raster here, we can look at the environments. We can set cell sizes, maximum extents. Down here, we have masks right here. And this is going to look a little different because I just installed ArcGIS 3.3. And so we'll be all doing that together after the break right here. And so what we can start to do, and I think I'm looking at some of the temperature data here, is we can create a brand new surface that looks like this based on the known value. So what is it right here? And I can click on this raster and figure out what it is based on these known values. Based on these known values. And those are important. Those are really, really important because we only have, 100 temperature stations across the state. Yeah, only 100 of them across the state. So we can't have temperature everywhere. So a lot of times when I ask Alexa in the morning, what's the temperature, it's probably not right because probably figure out where it is near the airport over where I live. And so we can see where it's higher, where it's lower. I could probably color these in a little bit better instead of this kind of snow looking or elevation looking stuff here. Now, the rationale behind interpolation is that observations are close together in space are more likely to have similar values than things further apart. And so we saw that a little bit with that PM stuff. And if I think of it, I'll bring up some of the things that we were looking at. As you move further away from an observed point, there's more variation. What's variation mean? What's that differences in them? And we had a student about 10 years ago. He works for Durham City. And I think he applied for a job up in the city of Oxford or something like that. And this was his thesis, or this was his thesis, where let me look at the different algorithms that we're looking at today. Which one has the most variation? How do we measure variation in this class? What descriptive metric do we have? What's that? Poisson, you're thinking too hard. Go back a couple weeks before that. Was it range? Even before that or after that? Mean, range, standard deviation. That tells us the amount of variation. And then the Z-scores and all that other good stuff. The reliability as we move from known points will decrease. And those are what we call control points. Trends within these data won't appear geographic, but these are going to largely be mathematical models. And so I think we were playing with those with the PM a little bit where we did different models and it was giving us like negative PM because this thing doesn't know that negative PM, negative particulate matter, doesn't exist. And so along one dimension here, we can see known values here and we can say, we can assume between 1 and 2, they're evenly distributed unless we know otherwise. And so it's the process to predict cell values for locations that lack sampled points. We're just filling in all of the missing points right here. So if we have something like this, all we're doing at a really, really fine scale is we're just filling in all the missing values here. Like over here, it's going to be 2024. I don't know what it is here, but we use these interpolation routines. And we're going to do a quick survey of the different interpolation routines, and then we will kind of go back and I'll let you, we're probably going to just start on the homework and do this. But this is rainfall right here. And so we create a surface that looks like this based on the known values. Now, if we only have one value right there, is this map going to have a lot of reliability? No. It'll do its best based on the known values because they're really mathematical models, but it's not going to be very good. And so when we look at something like this, where we're looking at ozone monitoring stations in California, you can say we're probably going to have good reliability over here because there's so many of them, not as good reliability over here. We're up in the northeast part of California as well. And so when we interpolate to raster, we convert vector points to raster, create a raster surfaces based on their values and particular fields. Now, once again, we can create masks because I want to create it for the entire state. I just don't want to create it for my extent of data. So we can make things kind of pretty here. And what we're going to be doing is we're going to be extracting these out for certain counts. but the power of the routine, raising it to a certain power, the search radius, the cell size, the number of points that we want to look at here. Because if we're doing like interpolation, how far away do we need to look for temperature? Like and that temperature in Asheville, is it going to be impacted by the temperature in Greensboro or Elizabeth City? Probably not. It'll probably be more impacted by the ones closer around it. So we're going to start talking about like weighted averages, because remember those equations for weighted averages. We alluded a little to those a couple of weeks ago when we talked about our cluster analysis. So we can look at air quality 1 week after 9/11. This is basically what we're creating from residences and known values. We create nice, pretty surfaces that look like this, because these aren't necessarily densities. These have a Z value coming out, which are going to be mapped red, green, orange, or whatever we have here. Now, the first one that I have, this is kind of like my favorite. This is called IDW. And it's my favorite because it's so easy. So kind of going back to like regression, I can explain and I understand the idea behind OLS, ordinary least squares analysis, which is a true mathematical model. Same thing with IDW. IDW, inverse distance weighting. What's the word inverse mean? Stick it in the denominator, okay? And so this says that our distance weighted interpolation values of unknown quantities will be influenced more by nearby points than further away. When we look at interpolation routines, we've got something called cribing, natural neighbors, spline barriers, trend, like just to create new surfaces. These are all the different routines, ways you could do that. So as you can imagine, the variability, you're going to be measuring the variability for some of the air now data is going to be really high depending upon which routine you use. Now, subject matter experts, what they're going to do is, maybe for air quality, they use a certain routine that everyone uses that, air pressure doesn't use, or hydrology, or rainfall, or so I'm not the expert on things like those. So IDW, a couple different input parameters that we can do is just say, hey, we're just going to pick the nearest 10, and we're going to average them up based on that, where the one that's closest is going to have a higher weight, the one furthest away has the lowest weight. Another thing is that we could do fixed radius, meaning I'm going to only average up the nearest however many within a certain distance. So if it's 1, it's 1. If it's 25, it's 25. So these are some of the different barriers and input parameters that we can utilize. And so I like this diagram here as well. So this is a cell right here that we're calculating. And then we can set the power equal to 1, 2, 3, 4. I know this value is C, this value is B. And so when we go to calculate this, the weight, remember that weighted average we calculated? You calculate weighted averages all the time with your GPA. Which class has the highest weight? One with the most credit. What point is going to have the highest weight? Likely. Because the 8? Well, we're inversing. So what's that mean? 4. So 1/8 versus 1/4. So that's what the inverse means. So the weight, this is going to have a higher weight than that one by a factor of 2 because this one's twice as far away. So when we calculate this whole weighted average points D, E, F, G, H, I, this is going to be weighted twice as much as this one because this is count 1/4, whatever over 4 is. Okay, 1/4 is greater than 1/8, greater than over 16, or whatever numbers that we're looking at. And so that inverse distance. Now we can weight it, we can do second order weight, meaning square it. So now this thing is going to have 4 times more of a factor than that one. So imagine having a class which has a weight of 4 versus a weight of 1. That's a 4 credit class versus the 1 credit class, as opposed to me having the 2 credit class versus the 1 credit class. That's the only difference when we start to raise the power. Now, if it's 3 times further away, it's 3 credit versus the 1 credit, or the 9 credit versus the 1 credit. So you're taking that 9-credit class, you better do well in that 9-credit class, too. Because that's gonna have much more of a weight. So that's what the inverse distance weight means. And it's just gonna be that big nasty with little sigma notation and little weights. We add them all up, but they do this for every single cell in North Carolina. So you can imagine how many different calculations we're looking at right here. So this is an example of, say, IDW1 versus IDW2. So we've got IDW1 right here. You can see your high temperatures down right here. I got 102, 93, 89, 90. There's one up there, 107. Ooh, that is really rough. And now what happens when we run IDW2? What did it do? Those nearby ones have a lot more weight here, especially with this 107. These areas around are going to be much more impacted by this 107 versus the previous ones where they were a little bit smoothed out. So this is the difference between IDW1 and IDW2. This we call it first order and second order. Okay. So the ones around it, about, not the ones, the bodies around it are going to have much more of an impact. The ones further away. I like that. I wish I could just skip all the other interpolation routines because I'm really good at IDW. I can kind of conceptualize it where that these splines are. And Daniel's going to start asking me some tricky questions about splines. I don't want him to. He's kind of asking me about regression stuff and what do I think of it, and but these spline ones, these are kind of more mathematical models. I like, I like these to create surfaces. They look pretty and a little bit smoother because that last one is truly mathematical. So if you do have that weird outlier, it does deal with that. But splines create a surface that passes through control points and has the least possible change. Standard deviation, variance, range, all those things that we talk about. So we create a minimum curvature surface. We have problems where there's little data. We have really steep gradients in data poor areas. So if we're looking at air now data in the eastern part of the state where we don't have a lot of data, you're going to run into problems. You're going to run into problems with data poor areas here. So we've got an example of our splines here. They kind of look, to me, look prettier, smoother, or whatever right here. But I think they're going to run into issues with those because what you're going to do today or this week for homework is that you're going to assess and evaluate which routine is best. Or you can write a thesis on it. And then actually, well, like I said, when we take data science, we're actually going to start bringing in data, reading it in and kind of running some algorithms on to see which ones have been automating that process. That would be a great, great dissertation, great, a great master's thesis. I'm kind of pointing to looking at some people who are good at Python. Yes, Daniel. Thank you for, and this is kind of one of my pet projects because the student who did it and we're going to be looking at his project, but we'll look at his project, but I even was a super strong Python programmer at the time and kind of gotten a little bit better at some of these things. This is IDW for Idaho right here, as you can, and remember that this whole middle of Idaho literally has no points. And then this is it using splines. And what we're going to do today is we're actually going to kind of fill in, we're going to create interpolated routines, and we're going to calculate the values and see how they compare because using one routine, this is 12.08 versus 14.59, 10.28 versus 14.82. Which one's the best? How do we assess and evaluate the best? I don't, that's tricky. The best. What is the best? Now, after the break here, we're going to talk about some of the metrics that I ran for a paper that we did this year. I'm trying to think. Who's on that? I think we got a couple of students that are on that paper, one of the PhD students. Okay, so some other things, and this is what we're going to look at. And this is actually the student's thesis. This is about 10 years old, but he was looking at temperature range between morning, mid, and max. And so we had some latitudes, some longitudes, how close it was to the nearest station, the nearest town. And basically, we used the first order IDW, second order IDW, natural neighbor, a couple other algorithms to figure out this was the actual value, and these are the different values that we measured for the different algorithms, and we kind of figured out what's the difference between these. That's what this triangle means. It stands for delta. So we looked at these, and so which one had the lowest delta or the lowest delta percentage? I don't know. Just kind of, gets into some of the things we're doing here. Other things we can create from these surfaces, contour lines. Lines of the same elevation. In this case, these are isohyets, lines that connect the same precipitation. So these are the same exact data using different interpolation routines that have entirely different contours. So we should create contour maps because people know what these contours mean. This surface is persistent, but these contours are kind of the same here. So we can create contours as well. So contour lines with barriers, because when we look at these temperature maps here, we don't have a lot in the middle of the state right here. And so why do they vary in techniques right here? Okay, these green are our stations, and then our towns here are in brown right here. So these are far away from existing stations, so there's going to be more variability with these. Another one that we have is called Kriging. You can read all that because it's just like, I'm not very good, this gets out of my skill set. I do like natural neighbor because it uses something called a Thiessen polygon. And these Thiessen polygons should be familiar right here. These are your Thiessen polygons right here, where we have sample points right here. We have a sample point right here. And basically we have the intersection, and we draw the intersection, and basically where all these intersections were midpoints. Remember, do you ever use a little protractor in math class? I used to teach, yeah. So the little midpoint or the bisector, and you keep intersecting these and getting rid of the extra points. These are called Thiessen polygons. So everything in this polygon is closest to this point. Everything in this polygon is closest to this point. Everything in this polygon is closest to this point. So it kind of approximates service areas. We're just talking about service areas, right? So it kind of approximates service areas, which are a lot easier than the service areas we're looking at with the drive time algorithm, even though drive time are much more practical. So these things are called Thiessen polygons. And basically for this area, it's just going to be a weighted average of the values in this Thiessen polygon versus this one versus this one versus this one versus this one. So it's just once again going to be a weighted average with these. And kind of in conclusion here, when we look at the variability of the Z values, now what's the Z value measure? Question, what's it measure? What's that? Change, yep. Variation from the mean. Okay, so our Z values look like -3 to 3. So with these different routines, your IDW, your spline is going to kind of hit the mark with all these different points with the Z scores, while Kriging is going to have more variability with your Z scores, where that IDW is going to kind of be right in the middle. That's why I like IDW so much, because we have less variability in the Z scores. I don't like looking at highly variable data because especially in nature with physical phenomena, with maybe economic or human or sociological phenomena, we have more variation that can be explained. But with physical phenomena, especially like temperature, air pressure, all those other things, you're not going to have a lot of variation as we move across place and space and even time. Okay, so when we get back, what we're going to do, we're going to open up exercise 8. We're just going to start working on exercise 8 together. I'm going to explain a couple things here. So we'll meet back here at about 6:15. We'll start working on that exercise 8. Because I like this, because what we're going to be able to do is we'll go through the process, but we can start to drop and drag these things. And if I think of it today, we'll drag these things into like a Python workflow window. So we don't have to remember what we did every time. We could just drop and drag these into there and then go from there. We can run this little model, change the input parameters and go from there, because if you're taking data science next semester, this exercise is right where we start. And we start right here and go from there. So let's take about 10 minutes here, take a break here. Make sure you open up exercise 8, and then I'll open up a couple things that we did with some of the PhD students, and we'll go from there.
The Israeli class that was for the tape for this one.
Yeah.
I didn't find that name.
Okay, let me look it up because they might have recycled it or something like that. All right, thanks.
It was like regression something.
Okay. Let me sign in and let me get going back. They always kind of retire some of these things. Oops. If not, we can just forget about that. Okay. 4130. This one or the Israel?
Israel.
Okay.
Maybe we get somebody.
I'm thinking, yeah, all right.
Or yeah, for the homework we just had recently, the Israel training.
The one I just gave that was due? All right, let's go back to that one. What week was that for? This one here? Introduction to Regression Analysis using ArcGIS Pro?
Mhm.
And it wasn't there.
I didn't see it.
It's about the.
Regression analysis. Okay. 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 I'll do that.
No, that's not it.
No, I took something off, but it might say intro.
Introduction to Regression Analysis.
That's the one.
Yeah, this is it.
Okay.
All right.
All right. Thank you.
Thanks, yeah. Yes.
It's gonna send you earlier. I got your email about.
Yeah.
So I clicked on it,
Okay.
and then it brought me here. Okay. Yeah. So it says I already applied.
Okay.
But this is the one I applied for last year.
Yeah,
Do I
okay.
need to withdraw and apply again?
Now, can you withdraw? No,
Yes, I can, but then it says,
no, don't. Let me. No, you won't do that. Let me get with HR. That's why we're doing this now. Let me see the job number. No, that's fine. That's,
it's 02.
I did something. What is it? Posting number. 02241P.
02241P.
Okay. What's the
Hey,
status?
Mr. Maroney,
Yes,
um, your screen is still on.
yeah, I know.
Okay, I just wanted to make sure, so like, I
Yeah,
don't know
it
if you're
is.
putting any confidential information there, just making sure.
Oh,
Just
oops. Yep, yep. That's right. Okay, thank you.
You're
I
welcome.
better. We'll stop for a second and we'll do that. Okay. Thank you. All right. I was like, yeah, I know I'm sharing my screen. Thank you. All right. It says you've already applied, right?
So the only option I have is to withdraw the whole.
Oh. You. 0024. P.
Yes. That's, no, 02241P.
022.
Yeah.
Is that right?
Even that one, 022.
Okay. So much. Okay. Okay, cool. Thank you. And we're gonna go back to here before.
Still, yeah. Credit center. It's been locked for a couple of days.
Which one?
The one beside yours.
The one besides ours?
Is that the credit center?
Yeah, it's graduate students, yeah. I think they've started locking it because they don't. Yeah, they started locking it. How about how about you all get a key? Or how's that sound? Okay. That sounds like a good plan.
Then I sent you the address you requested.
Okay, yeah, Cornwallis, it's right around the corner, right?
Yes, not far from us.
Okay, so do you drive there or
Me? No, I think it was.
you take a bus? Yeah. How long does it take you to get here?
30 minutes. That's considering wait time for the bus.
Oh, okay.
Well, straight drive would be 10 minutes.
Okay, so how do you get home tonight? Take the bus?
Yeah.
Not too bad. Is it too bad or not?
Except the winter when it gets cold.
So you've been here in the winter, right?
In January, late
Okay.
January. It was cold, but not so cold.
Okay, all right. And I'm gonna fund you through calendar year. So you might be taking not that many classes in fall. Okay? Or this, or this is your
Second semester.
This is your second semester, okay. All right, because I want you to keep working on code. Okay. All right, cool.
You're taking notes too?
No, I got
Oh, you never go there?
it. Yeah.
Okay. Yeah. Hold on.
Next for me, I'm a bit more quiet. That's sports. So.
Yeah. You don't want to write with me, you can write with me. Oh, yeah, I think. Seven. Yeah. Yeah. It's fine. Yeah, I wanted to make sure everyone fit in the tree.
I think it was.
Were they yours?
It's working as.
Yeah.
Small one.
Yes, it gets even more.
Yeah, I get some.
Yeah, yeah. I had a board here. You know, it's like you go park there. You know how small it is? Yeah. About that. We used to have a smooth room, before, it wasn't like it. Yeah, the tree one. So. Oh, that.
Weekends, maybe, by beer. I think it's a week. You see that? Well, that's just not feasible, not in this country. I've got 6 foot white, 6 Bud Light, and I love them tall blacks. Can we? Yeah. Yeah.
See, I would think it was in the house. You gotta find the fact, and you gotta work.
Stress them out though. I think you go there. Really? So I think she's okay. Oh, you let it down right first? Right. The elevator. Oh, yes, well, all over here.
Okay, all right, we're set here. All right. Okay, everyone can see too. All right. All right, we're back to sharing. Okay, cool. All right, so while we're sitting here, I want us to open up exercise number 8, homework number 8. This is what we're going to work on. I want for a little bit, I want to talk about a couple of papers in the under the modules. I've posted a paper. You can't see it or? Okay, all right. So this is my latest paper that we've got. It's called A Comparison of Raster-Based Point Density Calculations to Vector-Based Counterparts as Applied to the Study of Food Availability. Basically, what I did was I ran that point density analysis that I just talked about for Dollar General stores. That's it. And I compared it to other metrics that have been used in the past. Pretty straightforward. We did it. Now you could do it for anything. Fire stations, emergency centers, supermarkets, whatever you want, and just place the name, do the thing all over again, put in your own background research, and guess what? You got a paper. So this was published earlier this year. It was in 2024. So I've got two at the end, two grad students. If they were really smart, you know what they would do? Paper number 1, already done. That's what I'd do. Yeah, you know what I mean? That's what I'd do. Or utilize something like this. Okay. So this was done earlier this year. I talk about availability because a lot of times in some of the things, and I'm kind of speaking to Philip and Will right here, is that this is a map of dollar stores across the study area. I'm kind of a little intrigued with dollar stores just because they're cheap and they're kind of starting to fill the role of supermarkets, especially in rural areas. I live in an area in northern Guilford County, northern Greensboro, where we had a dollar store put up and everyone didn't want it because it's just the connotation with rurality and poor and whatever connotations you want to make, even though I could go across the street and pay twice as much for bananas or milk or, paper towels or whatever my wife asked me to pick up on the way home. Okay, and so what we did here was we created something what we call a density surface right here. Now, first of all, why did I show a map of all the points outside of the area as well? Respectability. Now, when I create a density metric, what do? I go to my little cell right here, and I also create a radius, right? And so this radius might include some of these points out there. And so if I got rid of all these points, Okay, and this is just done aesthetically, but if I got rid of these points, when I computed these, you see all these areas are really low. Why? Because I'm treating it as an island. When in reality, I might live here, zip over here to Dollar General store, whatever, on the way home. So this is my study area right here. This was done by a student named Samuel. Andy knows Samuel. You know Samuel, right? He's working for Esri right now, and he lives in California. So he did some really neat things. We'll talk about the assessment and evaluation piece in a second here. But all we did was just create a map that looked like this, and then I grouped them by block group. I didn't even do any associations with income, race, any of these other things right here. And I compared them to a bunch of other metrics at the block group level here. And so these are some of the other metrics that we've got right here. This is when I group that density service at the block group level, I get a value. 0.72, 0.93, 0.002, 0.27, whatever that number of units per square mile is or whatever. And then I compared it to this one. This is a 3 mile buffer, meaning for this one, what are the number of Dollar Generals within 3 miles of here? Just pro-flight distance. So I compared this map to this map. Now there's lots of other metrics. How else can we measure things? How else can we measure availability, proximity, access? Access in food desert studies is a little different because it takes on both, it takes on a time and transportation component. I mean, do you have, are you able to access transportation to get somewhere, and is the hours opening? And that's just, I think, a little bit more a question of semantics than anything else. So other things, how far is it? Pro-flight distance from the middle. And so some of the other metrics that we looked at, and one of the things about Samuel, which is probably better than me, is that he makes really good maps. And really nice maps, and they appear consistent, right? So the legend is in the same exact location, so I can literally just superimpose these on top of each other. And so this is with the 3 mile buffer, really easy to calculate. This one is drive time. How long does it take to drive from the center of each of these 242 block groups to the nearest Dollar General? Now we know the center or the centroid of something, we talked about centroids a few weeks ago, might not be the best approximation for something, but there's a lot of different rabbit holes we can go down. Drive time. Drive time is really hard to calculate. You know, just think about doing this 200 times on your phone here for all these points. Also, Euclidean distance. We talked about this. Near distance. We talked about with Philip. And then we also started to look at store density. What are the number of stores per square mile? Because we might have something that has 5 within it, but it might be really big versus really small. And then we look at another calculation, which is weighted by population. So the number of people per store within 3 miles. So I kind of estimated the population and then calculated the estimated number of population. So here, this area right here has a whole lot of Dollar General stores per person. Now, why does this thing stand out? What is so special about this area here? And this is a little weird here. I probably should have vetted this before, but what's so weird about this here? Weird thing about this is that this is RTP. So what's like the population in RTP? Really, really, really low. And so if that's in the denominator, what's going to make that what's going to happen to that density number? Pop up real high. And so it's relatively big. So it probably has a few Dollar General stores around it, but low population, that's going to shoot that thing up really high. And so basically what we did was we compared all these things to each other. And we kind of grouped these into most available, least available, neither. And so we started to compare this map to this map. And I use something called the Jacquard index to do this, to assess and evaluate this. I won't get too much into it, but I actually found that with the point density versus some of the other measures is that like this measured better than the other metrics. Like they agreed with each other about 3/4 of the time, because it's difficult to compare all these different units. But this is a perfect example of this density metric that we're looking at. Another thing that I've been working with the PhD students is that we went and downloaded some Air Now data. And I have the reference to it in exercise number 8, but this is Air Now data. We can download all this junk in the atmosphere. Carbon monoxide, PB is what, lead, nitrous oxide, ozone, PM10, PM2.45, sulfur dioxide? Okay, sulfur dioxide. I don't know, I assume all these things are bad, right? I assume they're all bad, but, so we can go to like PM10. This is the bigger stuff that gets stuck in your nose instead of the smaller stuff that gets stuck into your, gets into your lungs. But I can download all this stuff here for the entire state of North Carolina. I'm gonna click all the sites. I'm gonna get the data. I'm gonna just download the spreadsheet here. And these are all the readings for 2024. So these are all the readings for 2024. Download. Oh, here it is. Okay. And I'll probably just ask a couple questions about this because I'm going to show the final product right here. But these are all the readings here for 2024. We're looking, I think when we looked at it before, it was like 5,000. Here we're up to about, what, 3,000. Okay. 3,000 of these things right here for Millbrook. We have a latitude, we have a longitude, so you can see, and then we have different latitudes and longitudes. So you can see for this particular site here at Asheville, the lat, the long, the daily air quality index, and this was the measure. And then what can we do here so we can turn this into GIS data? Because I don't want 3,000 points on a map. How many different locations do you think are here? I'm asking the PhD students this weekend. But were there like 20 or 30, something like that, 23 or something like that? And so what we did was we ran a summarize on the latitude and longitude to count the number of times each unique latitude appeared. Because what are the chances that we're going to have the same exact latitude with 5-digit precision for another station? Really, really small. I probably could have done it on Asheville. I was just scared that there were multiple Asheville's or something like that. So we ran a summarize on the latitude. While we were doing that, we averaged up the longitude for each of the unique latitudes, which is going to be the same thing. And then while we were there, we averaged up the reading and the air quality index and maybe a couple other things so that we turned 3,000. And I think we also did instead of the average, we did the range, the mean, the median, the mode, all that other stuff that's available to us. And so we turned this table from 3,000 into about 21 stations that have a latitude, a longitude, the mean air quality, the range air quality, standard deviation air quality, the variance air quality, as well as the AQI, the air quality index. Now, if you have something with a latitude and a longitude, can you make a map out of it? Easily. And these are the maps that we made for these. And these are powerful maps because what we're going to be doing is just circling back to these right here. So we made these maps. Here are the air quality stations. And then, so now you can see the 21, 22, what is it? The 22 stations that we have. You can see how many different readings we have for each air station. We have the latitude, the longitude, the concentration, how many readings, the mean, the range, the standard deviation, the min, and the max for these values here. I didn't pull from the AQI. So some of these like negatives, you probably want to get rid of, vet these out a little bit better. I'll vet these out a little bit better, but these are taken from the raw data right here in the max. So now we can go and map these. And so what we did for this is we just ran some interpolation routines here. So we ran some IDW, we ran some splines. You can see some negative here for the splines, but this is an IDW map of the air quality index that we have right here. Okay, this is the AQI. And so what we got right here, this is where the air quality is best. It's where the air quality is worst. So I'm kind of excited about some of the things that I think we did with these, because I know we did some other things here, because this is what we're going to do for this exercise. All right, so now for this exercise, because this is what we just turned this raw data. So homework number 8 right here. Okay, we're going to look at a couple things. Maybe we'll look at the deer vehicle collisions, because I want to get us used to looking at some of the parameters here, because if we were just click and run, we're not going to get those nice pretty maps of North Carolina that look like this. Now, the first thing we have, these are our deer vehicle collisions. Okay, when you look at a map like this, what do you automatically say? There's a lot going on here. I'd like to make a nice density map. The same thing with like crimes, especially things like, carjackings or whatever, where, we want to avoid, we want to go to, avoid or whatever here. So let's start looking at the exercise. So I want to get to a good stopping point with that, because I want to kind of get us there. I've got a couple of videos right here that we can watch here. But homework number 8, this is particulate matter right here. Do I even have the deer vehicle? Oh, right. We'll deal with the deer vehicle collisions at the end. Okay. Boom. Okay. Sorry about that. So we'll deal with the deer vehicle collisions right here. So now we've got some states, and then we've got some PM locations. So this was taken probably about 8-10 years ago with the PM data. So it looks like they've kind of decreased the stations. So this is my PM data right here. Whenever I get data, I always right mouse click, open the attribute table. Let's see what the things we care about are. We got a latitude, a longitude, an average measure value, population, and a county. So just like you said before, I pulled these and I have an average PM value. Parts per million, whatever, parts per cubic meter. How do they measure air quality? Parts per million, parts per cubic meter, something like, I don't know what. I'm looking at people. Parts per million or something like that. I don't know. Okay. But these are the air quality measures. I could make a map right here. I can make a graduated symbol map that shows where they're higher and where they're lower. So if I can right mouse click here, go to symbology. Instead of single symbol, I can just say, hey, I want to make graduated symbol just for the heck of it. Instead of mapping longitude, I want to map average measure values. So you can kind of see where they're high and where they're low, right? Now, we look at Asheboro. Do I have an idea of what it is in Asheboro? No idea whatsoever. Even if I wanted to right mouse click here under PM sites, I can click on label. Right mouse click, I can click on label properties. And I can just label the average measure value here if I wanted to, right? So I can see a 10.73, 10.99, 9.74. I'm just kind of exploring the data right here. If I really want to. And I can right mouse click and just, get rid of those labels right there, because at the end of the day, what I want to do is I want to create a density surface and then extract out values. And so let's look at this map right here, because I think we just jump in real quick and start creating values real quickly for this, because I'm going to run the IDW first, and then hopefully we're going to get numbers that look like this. And then we're going to run spline, Krag, and natural neighbors, and then start to see how Asheboro's values differ from one to the next, so that you can look at it and say, I think this one's the best. This one has the most variability, the least variability, because how do we assess and evaluate which one is best? That's the $1 million question for everyone. You create a model, you create a tool, which one's the best? Philip, what are the relationships between income and proximity to emergency shelters? We got a lot of sub questions within there. How do we measure proximity? What test do we use? I'm always going to go back to the two-tailed t-test, but you saw that I branched out a little bit to that Jacquard index, where I just said 0.72, meaning this map compares with this map 72%. 62%, 59%. I just averaged up all of the averages. And so those are some simple assessment and evaluation techniques that only even deal with statistical significance and null hypotheses. So I created an interpolated surface. We're going to create an interpolated surface for IDW first, just because I want to make sure I'm doing this right. And they should be about the same here. Okay? Because I want to see what it is in Ashboro or Sanford or Durham or Wilson or whatever else. Okay? And so what we're going to do here, well, we're going to go to analysis. We're going to go to tools. And we're going to go toolboxes. And we're going to go down here to spatial analyst. Everyone should have spatial analysts. I hope you do, because I don't want to have to go and like open up things in the middle of class and permissions and all that other stuff. And then we got something here called interpolation. These are all the different interpolation routines that I'm talking about right here. So this is a step up from geostatistical analysis or spatial statistics. We have interpolation. So we got the IDW, Kreiding, natural neighbor spline, spline with barriers, topo to raster by file. I don't know what, I really don't know what topo to raster really means, to be honest. Okay, and then we got some of the other things up there with, contours and trend line and all that other stuff. So we're going to click on IDW. This stands for inverse distance weighting. So we're going to look at the different parameters that we have. What are my input points? They're going to be the PM sites. What's the Z value? What are we measuring? What are we mapping across place and space? Average measure, that average PM from the 326 readings to 272, because at some point in time, I took it from that big file for 2015 or whatever, 2014, 2015, whenever I took it, an average measure value. Output raster, it's going to store in a homework 8. We'll just call it IDW PM sites. The output cell size, we'll just leave it. Why is this number so small? What units are we working with here? Probably decimal degrees. So we got really, because how big is a degree? A degree is like 70 miles. So we got like 0.007, decimal degrees. So we don't want to make it really small because that's a lot of calculation. So we're just going to go this square 0.0077 degrees, this square, run our calculation, go over 0.0073 degrees, whatever that is, go over the next one. I think it's a little less than a mile, I think. But we got 55,000 square miles in North Carolina, so we're doing 55,000 different calculations right here, which will be fairly quick. Power, for now, I'm going to do first order. And this says search radius variable, number of points 12. What do you think that number of points means? Yep, that's how many PM sites it's going to base it on. So on my little 0.007 degree site, I'm going to look for the nearest 12. This one, look for the nearest 12. I can also specify distance, but I don't want to have to do math. So late at night, look at the degrees, I want to go 1 degree or whatever. I could do that because I can convert everything. I can change the projection to make everything like state plane. So we measure everything in feet, but we're just keeping the defaults for now. And then the order, what's that power mean? If it's twice as close, it is twice as powerful, not 4 times or any of that other stuff. Now, the other thing that I think is important under environments, let's click on the environments and let's look for cell size. To me, the 2 important things that I want are processing extent. And to me, this processing extent is going to be, and this is a new dialogue, so I'm kind of learning this myself because I just upgraded a couple weeks ago. So this processing extent is going to be let's do it for NC counties. So I'm gonna click the little folder right there. Oh, I'm sorry, the little layer thing, and then just NC counties. And now watch what it does. It puts in the top, left, right, bottom, whatever there. And then down at the bottom, I want mask. Mask, I'm gonna do NC County. So it treats it as a cookie cutter. Because if I just click all the defaults, it's just going to run to the extent of my PM sites, which doesn't encompass the entire state. So it's just gonna create a nice rectangle. I don't want a rectangle because there might be some places that are inside, outside, or whatever there. Okay, and so when I'm ready, I'm gonna click run. Might take a minute or two depending upon your computer. But think about what we're doing. We're running weighted averages for probably about 50,000 of these pixels. But even these things take a little bit of time. Okay, cool. I'll give everyone a minute here, but this is what I got. So now down at the zoo, I can get a good idea as to what it is there. And I can click on the little pixel right there and it can probably tell me if I turn everything off. It can tell me what the value of it is. They're not that county right there. Oh man, let me uncheck this thing and click on this little raster. And it'll tell me right there is what is the pixel value 9.55. And I can go over this one, it's 10.14. And I see this green one right here, 8.66, 10.54. And so I've got these right here. Now, my question is, I've got this table, right? I've got this table. What I want is, what's the value in Ashboro? Because notice, I just clicked on Ashboro and didn't it say something close to 9.55? Got it in the right track, so I'm kind of excited. Okay, 8.09, 9.32. I didn't make these numbers up. And if you zoom in enough, you can see the tiny little squares that they're composed of, right? Now, the one thing about this GIS that it tries to do, it tries to make these things look nice and smooth. It tries to make these things look nice and smooth, but when you zoom in and zoom out, you can start to see these squares take place. I like looking at the little squares myself because I think it's pretty neat. But the GIS tries to smooth them out a little bit there. Okay. And then you got some weird things right here like this or like this or like this. Those things probably come about because for these particular pixels, you've kind of picked a different 12 as opposed to a couple cells over in each direction. So you get some of these strange anomalies right here where you just get some strange anomalies. Now, my big question is, I want to see what the value is at all these other points right here because we don't know the value in these black triangles. Okay, we don't know the values. Now, are you going to have to go and hand click those? No. So we have something called, we have a function, I believe it's called topo. What's it called? It is called extract values to points. Okay, so now I'm going to go back to my analysis. I'm going to go to my tools. Does anyone know where extract values to points is in all these toolboxes? I don't either. So I'm going to type in the word extract values to points. Yeah, this is in spatial analysis. And what's it say? Extract the cell values of a raster based on a set of point features and records the values in the attribute table of an output feature. And I assume this next word is class. So let's see what we got here. So what are my input features? The cities, right? The cities. Because I basically want to see what the values are of these cities. And what's my input raster? PM sites. And then my output point features is called extract NC city 3. I'm gonna call it extract NC, and I'm gonna call it IDW, because now I'm extracting to that routine there. So when I go back and do it for nearest neighbor and cribing and splining and all that other stuff, I can differentiate between that. Okay. There's nothing wrong with running this because we got an idea what our value is going to look like. What kind of value should I get with this PM stuff? There should be 6, 7, 8, 9, 10, 11, right? Because once in a while, I'll just run the IDW on longitude and I'll get numbers like -82. And I'm like, that number doesn't look right. Why? Because I kept the longitude and I noticed they got bigger and bigger as I moved further east. So I'm gonna click run. All right, a lot going on in this left corner here. All right, what do I got here? Open attribute. So I got these 9 cities. Capital point, pop. What do I have all the way at the end? Does this ring a bell here? Let me sort ascending here. 9.531136. Close, right? 8.09 versus 8.12. So when I run the IDW, and if I want, I can cut and paste those right into this first table there, right? Right. Why are these different? Probably because I might have set the cell size to be a little different or calculated this. Am I going to care about 8.55 versus 8.53? No, probably not. How can I copy this stuff into Excel? Am I going to just start writing these here? Of course not. Okay. What am I going to do? I'm going to do a little switch. I'm going to copy. Let me open up an Excel right here. Boom. They're already in order, so I already sorted them. So here you go. Control C. And then right into boom. Just copy those straight in. And you can keep those original values if you want for this exercise, just because those are what I ran. I was giving you a good idea as to what you should be getting. Now, let's bust out a couple little tricks right here, not tricks right here, because that's a lot. Those are a lot of steps that we need to do. A lot of steps that we need to do. I got something here pretty cool called Model Builder. I'm just going to kind of show this real quickly, but I got this thing called Model Builder. Watch what I can do here. What was the first thing that we did? We ran IDW, right? So I'm going to go to my little analysis. Boom. IDW. Look at that. That's pretty cool. Extract values to points. Boom. So now, what do you think the little arrows mean? That's the workflow, exactly. This is the workflow. Okay. So this is the workflow. So I'm going to create an IDW. Now it doesn't have any color, so let me double click on this thing here. What do I have here? What are the input features? These are my PM sites. My Z field is what? The average measure. Okay. I'll set my environments again. I'm just kind of showing you this here. Or that, all right, I'm going to click the NC counties. NC counties, click OK. What just happened? It all got pretty colors. So what's the blue? What does that PM sites represent? Input feature class. It needs one input feature class. Are there instances where we need 2 or 3 or 4 input feature classes? Yeah, Yeah, when we run buffers or intersection reunions or some sort of more robust geoprocessing. Now I got this little yellow thing here, that's the process, and then what's the green thing? The output, exactly. And so next, I got to extract values to points. How many inputs are going to be for extract values to points? What do I need to run extract values to points? I need this raster that I just created, but what else do I need? A set of points, right? To extract to those black triangles. So what do I need now? Okay, input point features are going to be what? The cities. My input raster is going to be this thing I went through and just created. Cool. Wow. Now, oh, Will's really thinking, because now guess what you can do? You can cut and paste that, and guess what? Instead of IDW, let's do it for splining, fragging, and nearest neighbor, or second order. You know, I could be real slick too. Control C, Control V. Now this will start to get real ugly real quickly, because now I've got to create new output feature classes. I can't call it 5 because that 5 is for the top model. So I got to call it 6. And this is where you get real ugly real quickly. Okay, but I can create a 2 there, or a 1, or whatever I did. Done here. But there's a couple advantages to this. One of the things is that when you write a paper, I don't want to have a big paragraph, a big like page of what you did. I did this, and I did this, and I did this. No, what I want is that. I would love to see that. That's a lot less words than me getting bored really quickly. No, it really is. Okay. And if I go to my methods right here, some of the things that we did with our methods, we did data collection. We tried to highlight what we did, but what we really tried to do was like A, B, C, D, kind of explain these. People don't want to read big sentences of what you did. So you can see what we did here. And I think our student, he wrote a couple of equations. This is what point density is, store density right here. This is what we calculated. Really nice summary. So one of the advantages is this. Okay, now if I want, I'm going to delete this for now. But IDW, we can create a nice little, I don't have to remember what I did. And you can go do the same thing for fragging, splining, nearest neighbor, and whatever else, because either fragging or splining is going to have some issues. You have a question, Cameron?
I was gonna ask if you go through the crank, because I was trying to go through, and I was getting errors.
Yes, fragging, you're going to get errors because fragging doesn't go out. Fragging is a truly interpolated process. What does that mean? You can't figure out areas you can't figure out regions outside of the bounding box because there are no values there, right? So it's based on what it knows. And so it's truly interpolative where that IDW and with a Kriging or splining you had issues with? Kriging. You did?
Yeah, when it says unable to allocate memory, so I'm guessing it's computer.
That might be a computer thing, but we'll also run the spline where it's extrapolative. What does extrapolate mean? To go out further based on known values, where that interpolate is to figure out the missing values with known parameters. Okay, where you have a bounding box. So I don't want to bore you too much with things like that. Okay, but now we've got this thing right here. This is pretty cool. I can right mouse click and I can run this thing if I really want to. So I can run this model. I can variable, I can paste, create a variable. I can go to my little diagram right here. Oh, model builder, I'm sorry. Model builder, I can save this model. I can export it to Python file. I can export it to a graphic. So now I write my paper. I've got this sitting right there. I can export to a Python. What's this? You all just wrote your first Python program today. You didn't even know it. Because I've never written a Python program in ArcGIS Pro from scratch. I always start with, I want to do this. I'll throw this into look at this thing. Look at all this stuff I just wrote. I got the whole code right there ready to go. Look how great I am. I've been busy. I got rest here, but now I can go and cater all these because some of these are hardwired, like it's looking for NC County. Wouldn't you like to write a program where the user goes and picks the input file? And that's what we do in our data science class where, hey, you pick the input file, you put the output raster or whatever you want to do. Or what I do is, hey, let me throw this into a loop and bring in the rasters for 2015 and the 2016 and the 2017 and the 2018 and 2019 and just put it into a nice little loop and run 10 years worth of data and me look really, really smart with all these outputs and extrapolations. And I bet you there's ways that you can cut and paste all this stuff right here that I could make really easy. Probably spend about the same amount of time doing it right in the program, but you look really good. To me, this is where you start to get into master's or definitely PhD stuff here, where let's just automate the stuff. Let's pull it from some site for a year's worth of data, analyze this stuff. Because originally what were we doing? Summarize. Can you do a thing called summarize? That's what we got here. SUMM. Boom. Summarize that attributes. What do we have here? Okay, we can summarize attributes from our original data. What else can we do here? Add XY. And then that comes into the PM sites that we've created. So we got, look at this stuff here that we can do. Pretty powerful, very, very powerful. That student Cedric, who wrote the original data, this is what he did for an internship. 1 year working for DOT, DOQ. He just wrote these really big models. And so now when you go back to these, all right, I just got to change the name of the output stuff so I don't have to remember what I went and did. But you can go and cut and paste these, change the output parameters that are feeding into these, or just change IDW, change that thing to a nearest neighbor. The same exact thing. I get kind of excited about these, but we'll run spline. How's that sound? Okay, let's run the spline, because if you get problems with nearest neighbor or crying, I'm not gonna get too mad about it, because those are some of the things that you're gonna run into when you run into these extrapolated processes. All right, so we're gonna go and do one more here. But you can see there's some really neat. I like this model builder. More importantly, so you can show people exactly what you do. I'll look at that any day than just this is what I did and that, and it saves time, space, and energy. All right, so let's get rid of this one here. We'll get our counties. Let's go back and run interpolation. Let's run spline. Okay, what are our input features? PM sites. What's the Z value? Average measure. Let's leave everything else the same. And then under environments, we'll make it for NC counties. And our mask is NC counties. All right, is there something I'm, we all good here, playing catch up? Okay. All right.
It says this.
Oh, I knew that. I was just making sure everyone was paying attention. Thank you. Okay. NC counties. All right, here we go. Here's our spline. You like it? You don't like it? What do you think about it? Look at up in Elizabeth City up here. We're getting values of 18. Look at out here in Western North Carolina. We get values of -4. Not good. Now, my $1 million question is here, wouldn't it be really cool if I just subtracted this surface from this surface? Wouldn't it be cool to see like where they're high and where they're low? This looks pretty neat, right? Now in raster class, this is really simple. It's called raster algebra. So we're going to go to analysis, and you don't have to do this one here because I think we did this with PhD students a little bit, right? But when you take raster class, this is where you live, right here. So under raster calculator, we can do the spline minus the sites, create a brand new surface. Oh, I gotta put a little minus sign. Look what I have here, the difference between the splining and the Kriging. We have differences of 14 up to 9. Same, the thing I stress is this is the same exact data that we're looking at. We're just interpolating and extrapolating it differently. Just think about, the same data, kind of like when you make maps. Now, for me, I don't like these maps here. So I don't like this color here. So I'm going to do some type of, let's do some little classify here. $12. Okay. All right, I guess it doesn't like me. And so what do you see here? These values are going to be really close to 0, near our control point, near our known values. So what we'll do here, we'll do the same thing for the splining. Try running the Kriging and the natural neighbor. The natural neighbor might not like you for all of the stations because it gets outside of that skill set. It might not even run it for you. So in some cases, like for Boone or for Hendersonville, it might say can't run it because our furthest west station doesn't have it. So play with some of the parameters right here. And then what's the range of values for Durham, for Sanford? Which technique works best? Now, if splining doesn't run, then definitely spline won't be the answer. Or Kriging. I'm a big IDW person. Like that's, to me, I like IDW, but it doesn't look as smooth and I can understand it, kind of like OLS. All right, and then what last thing we'll do here is we'll create, Create an interpolated surface map. Oh, cool. Look what you're gonna do here. Straight from the EPA site. We've got some people here who already did this before. Okay, but we have a density map right here as well. So we've got these surfaces right here. So now, circling back to the bear sighting, these aren't bear sighting, deer collisions. We can go to analysis, tools. We've got something here called density, kernel density, line density, point density. I can double click on point density. Deer collisions. Where's the Z score? Where's the Z value here? There is none. Because all we're doing is just looking for the concentration of points here. I'll just kind of run a quick and dirty map right here. But now what we have here is deer collisions and the density of these. So where it's higher, there's more of these. You notice these squares here? These are your pixels that I created. You could change the resolution on these. What do you notice about the dark areas? More points. What do you notice about the lighter areas? Less points. Right? Most people want to look at something like this as opposed to the other thing. So I just want to make sure we understand the difference between density and this map here, which is interpolated values. Make sure we know the difference. Okay, this density says, hey, the density here is 1.7 deer vehicle collisions for every square mile. Purely mathematical. While something like this says, based on the value, the air now data, the PM data is 7.32. How do we feel about that? Feel good? This is the last homework of the year, so. And then I kind of ask you to go and download some of that air quality data and use your GIS skills to make a couple of interpolated surfaces. I know a few people have already done this. Okay. So we use a couple of these different techniques. Oh, feeling good about this one? I think we answered a lot of the questions here. I kind of gave a sneak peek for some of the modeling stuff here, which I like. You know, things like this here where you can really turn this into some really high quality Python programming with really little programming skills. I think I'm done. Is everyone else here done? Okay, good. Me too. All right, I'll be gone Friday and Saturday at a conference. And so I'm probably going to be, I don't get offended if I don't return your email because I'm going to be committed to a retreat and a science festival out in Greenville. So should be good. All right, so see everyone online. I'll see you all later. And everyone here, I'll see you all later. And I'll make this due in a week from today. And I'm kind of forcing you to do it next week so that you could just spend the next month on your position paper and not blame me for making multiple things due on the last day of class. So you can just blame me for turning it in early and then just working on the paper, because that's a big priority. So I'll see you all later.
Thank you.
All right, see you, Juan.
Okay, Mr. Maroney.
Yes.